we're going to start. So there's different, at certain points in the notebook, there'll be situations like this where there's an exercise and it prompts you to put in your solution, and then there will be a collapsed cell that contains the actual solution of the exercise, or one potential solution of the exercise, I should say. So you'll see that pattern showing up. So I think that's enough to get started. I'm going to pass it over to James for the overview.
Yeah, sounds great. Thanks, Julia. Let me share my screen real quick. Great. So you guys should be seeing the exact same thing now on my laptop, the overview notebook. Also, just as a heads up, I have my camera is not on my big screen, so I'm going to be looking away from everyone. So just as a heads up, you can expect that. Great. So here's the welcome notebook that Julie just presented. We're going to move over now to the overview notebook here. So before diving sort of more deeply into Dask's internals, we want to provide a high-level overview for Dask more broadly. I'm sure there's a wide variety of backgrounds in the audience, so it'll be good to kind of lay a nice foundation up top. So that's exactly what this notebook does. It goes through a high-level summary of Dask, why you might want to use Dask, and then we talk about some of the APIs, sort of the user-facing parts of Dask as well. So first off, what is Dask? So Dask is a flexible, lightweight, open source library for parallel computing in Python. It's totally community open source project. Here is the source code for Dask, and its documentation is linked to here. Dask was designed to scale the existing Python ecosystem, and we'll talk a little bit more about what that means later on in this notebook. So instead of talking about what Dask is, maybe a more important question is, why would you want to use Dask? Dask enables you to run your code in parallel. It also enables you to take existing workflows you may have and scale them to larger than memory situations. So it uses APIs that you're familiar with from NumPy, Pandas, and Scikit-Learn. And this is sort of at the core of what we mean by it scales the existing Python ecosystem. You have some NumPy and Pandas code already out there that you're using. You can switch those over to their Dask variants, which look incredibly similar and scale to, instead of processing, a single Parquet file on your laptop, to processing, thousands of Parquet files on a cluster, where the code looks very similar. So yeah, like I said, this allows you to scale existing workflows with minimal code changes. Another great thing about Dask is that it works equally well on your laptop, on your local system, equally well both on your laptop and scaling out to larger clusters. So you don't have to switch your tooling when you're sort of maybe experimenting locally with smaller data set. You then want to go to your full workload. You don't have to then switch your tools, the tools you're using, to something else when you switch to using a cluster. And then finally, Dask offers great built-in diagnostic tools. This is a huge reason, or rather, this is a really nice feature that the people who use Dask tend to really enjoy, and we'll demo those later on. So generally speaking, you can think of Dask as being composed of sort of two main APIs, or two main ideas. The first is that of what are called Dask collections. So these are things like Dask arrays, Dask dataframes, Dask bag, Dask delayed, and the futures interfaces. These are sort of all the user-facing APIs that Dask users use to set up their computation. And we'll see a bunch of examples of those in later cells in this notebook. All of these APIs, they fit slightly different. Like if you're doing indie array workloads, you'll use the Dask array API. It looks very similar to NumPy. If you're dealing with tabular data and wanting to do lots of joins and group bys and sort of exploratory data analysis, you can use Dask dataframe, which is similar to Pandas API. All of these APIs under the hood will generate task graphs. So you use these collections to generate task graphs. And we'll talk about those a lot in much more detail later in Julia's section of the tutorial. These task graphs are basically, these are all lazily evaluated. So you use these APIs to kind of set up your computation. It doesn't actually perform the computation immediately until you ask it to say, hey, I have the thing I want to compute now. Go ahead and compute it, Dask. And Dask has several schedulers. There are single machine schedulers and a distributed scheduler that you can use to run your computations on a cluster. And these schedulers are the things that actually go through and compute your task graph potentially in parallel. So the two main parts of Dask are these collections to generate task graphs and the schedulers to actually compute those task graphs in parallel. So let's talk a little bit about task graphs. Here is maybe the world's simplest example. So this code here has no Dask code at all. This is just sort of pure Python to set the stage. So I have some increment function here, which takes in a variable and increments it, returns it +1, and then an add function. I then define a couple of variables, a and b, which are 1 and 12, and then I can increment both those things to produce c and d. So in this case, I'm incrementing 1 and incrementing 12, so it should be 2 and 13. Then I can add those things together, which 2 and 13 should give me 15, and I can print the output here. So that's how I would express this particular computation in Python code. We can take that Python code and sort of transform that into a task graph. So which is illustrated here. So here, circles represent Python function calls, and the little square outputs are the results of those function calls. So here you can see where I'm calling my increment on A, increment on B, producing output. Then I'm passing those into my add function to produce the final output here. So you can hopefully see the mapping between the code up here and this task graph down here, this visual representation. So we're getting these interdependencies between the tasks. So for instance, before I can compute the add task here, I have to first compute 2 increment tasks here. I then take the output, pass them into the add function. So that is sort of a simple example of what a task graph is, and it sort of captures the basics or the essence of the task graph. Let's now talk about how we will compute these task graphs using Dask's collections. So the first one I want to talk about is Dask arrays. So Dask arrays are chunked in-dimensional array objects. So you can think of Dask arrays as being sort of a parallel chunked version of NumPy. So for instance, if you have a 2-dimensional array, which is sort of what the image down here is displaying, the Dask array itself is actually composed of several chunks. So you can see I have this chunk, this chunk, this chunk, so on and so forth. These are all sort of chunking up my data set. And each of those individual chunks itself is actually a NumPy array. So you can think of a Dask array as coordinating a bunch of chunks of NumPy arrays in this case. And Dask arrays actually implement a large subset of NumPy's API using blocked algorithms. We'll see some examples of block algorithms in a second, but block algorithms basically work on these individual chunks themselves instead of working on the entire array. So we don't have the entire array in memory. We have a bunch of several small chunks in memory, which we can then perform our computation on. And the result of the blocked algorithm should give us the same result as if you had the entire array in memory to begin with. And for many purposes, Dask arrays can serve as a drop-in replacement for NumPy. So we can import NumPy as NP, and this sort of the corresponding Dask import would be to import Dask array as DA. And so here we can go ahead and create a NumPy array using a range. So 1 up to, but not including 50, in step sizes of 3. We produce this NumPy array. We can do something really similar in Dask, except we also specify a chunks option. So here, so I'm printing out the type of this Dask array. So Dask arrays have really nice Jupyter HTML wrappers. So if you just print a Dask array in Jupyter, it'll give you this nice little display you see here. So it tells you information about the entire array itself, the giant Dask array, and then also information about the individual chunks. So these are the NumPy arrays. So you can see the entire array here has a shape of 17 elements, and each chunk has length 5. So you can imagine I have a 1-dimensional array of size 18. I've kind of divided this up into chunks of size 5. And altogether, there are 4 of those chunks. So yeah, we have some nice information like D type and number of chunks, things like that. Much like NumPy arrays, Dask arrays also have D types, shapes, sort of all of the similar attributes you would expect an ND array object to They're also, as I've mentioned before, lazily evaluated. So this is the underlying task graph for this Dask array. So we've taken a Dask array, like the Dask A-range version. Underneath the hood, it actually just calls NumPy's A-range several times, once for each chunk. So each of these function calls here, that's actually the good old-fashioned NumPy A-range that's producing the output chunks here for our arrays. So we can see I'm going to call it first. So what is this in chunks of sizes of 3? So this will be like 0 up to, what is that, 4, so on and so forth. So we'll just call A range with the appropriate start and stop bounds to produce the chunks of our Dask array. Everything here has been lazily evaluated. We haven't actually done any computation. We've just set up this task graph. So Dask now knows how it could compute this array if you ask it to. So to actually go ahead and compute the array, you can call its .compute method. So now that actually goes through, computes this task graph, and returns the result, which is here just an old-fashioned NumPy array. So you can use Dask's API or Dask's NumPy API to do many of the same operations you would already do today with NumPy. So we support arithmetic and scalar mathematics, reductions, slicing, array protocols, some linear algebra, all that good stuff. For a full list of what is supported, I recommend going to the Dask Array API docs. You'll see all these methods here, arccinch, arctan, around, at least 1D, all these similar functions to what you see in NumPy. You see the list kind of goes on and on. So a little bit about blocked algorithms now. So let's take let's generate a new Dask array. It'll just be a random array of chunks size 5. And do some computations. So what I can do here is compute the sum of this array, for instance. Let's first visualize the task graph. It looks something like this. So you can see I generated a random array and then called sum on it. So what the underlying blocked algorithm is doing is calling NumPy's random sample, this 4 different times. This is for each of my partitions in my Dask array. I then call NumPy sum on each of those random arrays that are generated from random sample. And then to get the total sum, I then take the individual sums of each partition, sum all those together to get my final sum at the end. So this is one example of a blocked algorithm. And notice I just used the NumPy API and didn't have to worry about the blocked algorithm itself. I didn't actually have to implement that because that's what's implemented in Dask for us. To compute that sum, we can just go ahead and call the compute method. I should also mention, right now we're just calling compute. We'll talk more about this later in the tutorial, but for now we're just ignoring some subtleties there, which we'll revisit later. So I can do, you can build up really complex task graphs using just the simple NumPy API. So here I'm generating another random array. This one's 2-dimensional, and then I can take this array, add it to its transpose, take the sum along a certain axis, and then get the mean. That generates this task graph. So we're seeing, we don't need to dive into it too deeply, but the take-home point here is this performs this computation for us with blocked algorithms, and we didn't actually have to write this graph. All of that's already taken care of for us. So we can call compute, it'll compute this graph, go through, compute all these tasks, and there's our result. One thing to note is that Dask will be, block algorithms allow you to only load in certain parts of the array at a time, and when they're no longer needed, meaning like this result, it isn't used anywhere else further down the line in my task graph, I can then free that memory. So this allows us to perform computations that are larger than the memory stored on our machine. So for instance, here I can take an array. I'm just going to go ahead and get this kicked off. Here I generate a large array. It's actually 16.2 gigabytes. In size if I was to load the entire array into memory. My laptop is where I'm running this, and this actually only has 16 gigabytes of memory. If you're running the tutorial on Binder, most likely you'll have even less memory available, maybe only like 4 gigabytes of memory, and you should still be able to run this computation on Binder, for instance. So it's going to take a minute because we're kind of going through the graph and allocating a bunch of memory and then freeing a bunch of memory as we go. But we will eventually be able to get through this computation, which is, I don't know, really cool to see that we can do a computation on a data set that is larger than I can fit in memory than on my laptop. And I think we're past sort of the bottleneck in the computation. And there we go. We were able to do this computation on my laptop. The next collection I want to talk about, I'm going to go through relatively quick to just for time's sake, is Dask dataframe. Much like Dask array is to NumPy, Dask dataframe is to Pandas. So Dask dataframes are a collection of Pandas dataframes partitioned along the index. So here, each individual partition of a Dask dataframe is a Pandas dataframe. So much like how we import Pandas as PD, sort of that's like the canonical way to import Pandas. The canonical way to import Dask dataframe is import Dask dataframe as DD. Much like Dask array implements a lot of the NumPy API, Dask dataframe implements a large portion of the Pandas API, including all of the IO functions we know and love, like read CSV, read Parquet, etc. So here in this cell, I'm just going to really quickly generate 5 sort of random Pandas data frames and write them out to disk using Pandas to Parquet. So none of this is Dask. This is just Pandas generating some data frames and saving them to disk. I can then use Dask to read all of those files that I just generated, all 5, into a Dask data frame here, which also has a nice HTML wrapper. So you can see here, there are 5 individual tasks. There's going to be 1 for each of these 5 files that I just wrote to disk. So you can look at the number of partitions, how many individual Pandas data frames are comprising my Dask data frame by looking at the in partitions attribute. In this case, there are 5. I can visualize the task graph. This looks really similar to the previous A-range example, only here we're calling each partition we're calling Pandas read Parquet function here to produce the underlying partitions in our Dask data frame. Large swath of the Pandas API is supported. And again, we can use the Pandas API, for instance, to take our Dask data frame, select a column, and take the mean of that column. And that will produce a task graph that looks like this when you call the visualize method on it. So didn't have to generate this graph at all. You can kind of get a sense for what's going on here. We have our read Parquet to generate the partition. We then selected the X column, that's this get item call. And then we end up for each partition computing an aggregated count and like number of entries and an aggregated sum so that we can take the ratio to produce the mean of the entire column in a blockwise or in a blocked algorithm fashion. So we can call compute and voila, there is the result. So that's Dask array and Dask data frame. There's also Dask delayed, which I guess for time's sake, I'm going to go through relatively quickly. Here are some functions. This has no Dask code. I've written an increment function, double function, and an add function, and added some sleeps to them just to sort of simulate some actual computation happening. Otherwise, these functions would happen very quickly. I then have some computation here that I do. I have a list of data. I loop over it and do some computations. I increment the data. I also double the data. Then I add those together, and I'm pinning that to some list that I eventually take the sum of. And we can see when I ran that cell, it took 5.5 seconds to run. If I wanted to parallelize this operation, this particular computation, this for loop lends itself nicely to parallelization. I can import the delayed decorator from Dask. I can then take my same functions as before, my increment, double, and add, and I can, for instance, just add a single line of code which decorates them with this delayed decorator. What this does is produce a delayed object that acts very similarly to our original function. It just sort of delays the execution. You can take this new delayed function and pass in inputs, and that will produce a delayed object, which when you compute will actually evaluate the function itself. So here I'm incrementing 3, and it produced 4. The nice thing is that you can compose these delayed objects. Whenever you take a delayed object and feed it to another delayed function, it will build up a task graph under the hood. So you can see here, I'm taking my lazy increment and kind of doing it twice, and it's building up this task graph for me automatically. I don't actually have to really think much here about how I should parallelize things. I just decorate my functions and builds up this task graph automatically for us. So here I'm taking all 3 of these functions, delaying them, and then I'm having the same cell as before, that I'm running here, we can see that ran almost instantly. I'm just now using my delayed versions of the function. That's because this actually produced a delayed object as the result. It didn't actually do any computation here. This is all lazily evaluated. Here's the task group or the task graph that is produced. So you can see here, I'm looping over things. I'm taking my increment and double function. I'm then passing those to add. Those are ultimately going to my sum function. And we can produce this full task graph just by basically decorating these functions with delayed here. I can then compute this task graph here, and that took 2 seconds or 1.77 seconds, where before it took over 5 seconds. That's because we were able to compute various branches in this for loop in parallel at the same time. So that's it for the collection side. So we've talked about Dask array, Dask data frame, and Dask delayed. I'm now going to talk a little bit about schedulers. So here's a nice little animation of a Dask scheduler going through some task graph and actually computing things. In this image, the orange squares, those are things that are currently being computed, and the blue squares and circles are things that are no longer needed. They've already been computed. We're able to free up that memory. So sort of the red things are the things that kept in memory at any given instance. So you can see how we have a much lower memory footprint here by using these block algorithms. There are a few different single machine schedulers which are offered. So we're going to kind of now circle back to when we called compute. So before, when we had a computation, we would call compute, and sort of just each collection, array, data frame, and delayed, all have their own default scheduler that they use. So if you don't specify anything, they'll use their corresponding default scheduler. You can also specify if you would like to use a multi-threaded scheduler, multi-processing scheduler, or a single-threaded scheduler. So each of these 3 single machine schedulers are sort of computed in the individual tasks are computed in on some resources. For the multi-threaded scheduler, they are computed in a local concurrent features thread pool. This is actually the default scheduler for Dask arrays, data frame, and Dask delayed. So all the things we talked about by default will use a thread pool to compute things in parallel. You also can choose to use the multi-processing scheduler, which will use a process pool, a concurrent futures process pool executor to compute tasks. And there's also the single-threaded scheduler, which computes things in the main thread. It doesn't compute things in parallel. This is actually really useful for debugging. That's sort of the main reason you would want to use the single-threaded scheduler. So to swap between the different schedulers, there are a few different ways to do it. You can globally set the default scheduler for all compute calls by using dask.config.set. Scheduler equals, in this case, threads. That means after this point, any computations that you just call compute on will automatically use the multi-threading scheduler. You can also set the default scheduler for a given context by using basically the same dask.config.set, but using it with a with statement in a context manager. So any computations that occur inside this block will use the multi-processing scheduler. You can also be a little more fine-grained and say for a given compute call. So before we were just calling compute with no keyword arguments, you can say, I want this particular compute to use the multi-threading scheduler. And then the last little piece of information is you can specify the size of these thread pools and process pools by using the numWorkers argument. So by default, it will inspect the number of cores you have, the number of CPUs you have locally available. I think it'll use that will be the thread size for the thread pool or the process pool. If you want to use something different, you can manually specify that as well. So for instance, here I can say, I want to use a thread pool that has 4 threads in it for this particular computation. Okay, great. And with that, that brings us to, those are all the single machine schedulers. And that brings us to the distributed scheduler. So despite having the word distributed in its name, a better name might have been the advanced scheduler, because the distributed scheduler works equally well both on our local machine using local threads and local processes, or you can also run the distributed scheduler across multiple machines using threads and processes that are actually located on different boxes or different machines, and we communicate between those machines. We're not going to talk a ton about the distributed scheduler here in this overview notebook. We'll talk about that more later on in the sixth notebook. So for now, what I'm going to do is just from dask.distributed import client, and instantiating this client creates one of these distributed schedulers for us. So I'm going to use the Jupyter Lab extension over here. You can click the little Dask icon there, and then click this magnifying glass to attach to the scheduler. This allows us to embed all the various plots we see here. Look for the task stream directly into Jupyter. So these are those really nice built-in diagnostics that I was talking about that Dask offers. So so yeah, here we can see I'm going to do some array computation and call compute, and we'll see that our computation starts firing off over here. I can see all the tasks in the task stream, or all the tasks rather in the computation, sort of flying by here. Each of these little tasks represents an individual Python function being called. In this case, we're doing things like transpose and sum. So a lot of these functions will be, like NumPy sum, NumPy transpose, things like that, NumPy mean, etc. I'll maybe run that again just so we can see it. And then we get the overall progress of all of these functions that are running down here. This is a real-time view of what's happening on the cluster. And these are just two of the plots that I'm showing. There were a ton of other plots over here that I highly recommend you explore. The last thing I wanted to talk about was the futures interface. This is a new interface for producing task graphs that is only offered if you're using the distributed scheduler. So Dask array, Dask dataframe, Dask delayed, all those other things work perfectly well on the distributed scheduler or on a single machine scheduler. The futures interface is only possible with the distributed scheduler. So here again are our friends, the increment, double, and add function. We can run these functions locally in Python by just calling them, or we can run them on our cluster by using client.submit, and then the name of the function or the actual function you want to run, and then any inputs that you would normally pass to the function. Those could be positional or keyword arguments. So here, before I was running inc1, so I would say submit inc1. That'll return a future object, which for those who are familiar with the concurrent futures interface will be familiar. We see initially the status of this thing was pending, and eventually the status will be finished. We submit this task to our cluster, eventually it runs it, and to get the final result, we can call result on it. We can see here is the result of that increment call, or rather here is the increment task that was processed on the cluster, and here is how you would get the result from the cluster by calling .result. Much like the delayed interface, you can build up computations sort of quite easily by passing these future objects to other client.submit calls. So I can take increment, produce a future, and double and produce another future, and then take those two futures and actually pass them to the add function to produce another future. And this ends up resulting in a few more tasks being run. You can see here's the double task, here's the add task. I can then call result to get the final result at the end. We can also submit many tasks and they will be at the same time, and they will all be taken care of. So here's a big for loop. I'm going to submit a bunch of tasks and then call sum on the end of it. So you can see now we're submitting a bunch of tasks. That happened almost instantaneously, because remember, this is just like firing off work to the cluster, and then the work is happening asynchronously in the background, all the stuff that's happening over here. Right now, total is still pending. I've noticed my cluster has kind of stopped moving, so maybe I'll refresh this cell, and oh, the status is finished, so I can get the result, and that happens to be the result for this computation. I'm not going to go through these cells and for the sake of time, but one nice thing about the futures interface is it allows you to dynamically build up computations on the fly. When you're using Dask delayed, you can definitely customize, or you can definitely parallelize custom code, but you have to build up your task graph ahead of time and then call compute on it. The futures interface allows you to dynamically continue to build up the task graph based on results from previous tasks. That's sort of what these two cells here, or these few cells here illustrate. So that was a whirlwind high-level view of Dask as a whole. And we're now going to move over to the notebook 2 custom operations I, P, Y, and V. And I'll, at this point, pass it over to Julia.
Hey, James,
Yeah.
real quick. I don't know if I'm a noob at this or what, but how do I open the like sort of windowed view of Jupyter Lab?
The window
like
view of Jupyter Lab.
Have the tabs like side by side, for instance, instead of like overlapping.
Oh yeah, so like I'll open up the notebook that Julie's going to go to, number 2. So like you can go here, double click on that. That will have it here,
sure.
Like right next to it. You can kind of take this and like drag this around, and you'll see like it'll kind of pre-populate it. It'll be blue. It's like, do you want it to snap there? Do you want it to snap here? I want it to snap there, so I'll let go.
Oh, I see. Okay, cool. Easy.
And it'll do it.
Yeah, thanks. I've never done it before. Who knew?
Yeah. Good question. Cool. All right, take it away, Julia.
All right. So I am going to be talking about custom operations to start with. So we talked about, James mentioned that there's all these different API, that there's a very complete API that mimics the Pandas API, the NumPy API, and provides all these standard operations like mean, max, value counts that you would expect to have access to on data frames and arrays. But sometimes in more niche use cases, the predefined algorithms aren't exactly what you need. So you can always wrap arbitrary functions in Dask delayed to parallelize them. And that's often the simplest, most straightforward solution. But it's not always the fastest solution. It's actually often the slowest solution because Dask delayed doesn't understand the organization of your blocks. So when you need something that when you need to write a custom function that operates on the blocks in the order that they are in your array, you can use custom block computations. So we'll talk through some of the different options you have there. In this notebook, we're going to be focusing mostly on Dask array and a little bit on Dask data frame, but some of the same principles apply to Dask RAG as well. So block computations operate on a per block basis. So for every block, which you can think of like a NumPy array, the block and chunk are the same. So you will apply the function to that block, and then the output will be will just be those output blocks with the function applied. So the shape of the input will be roughly the shape of the output. So these functions are Dask array map blocks, Dask data frame map partitions, and there's also Dask bag map partitions. You can find the documentation at these links. So this is a straightforward case of map blocks on a Dask array. So we're going to construct an array. We can take a look at it. We can see that it has this shape of 6, and it has 2 chunks each that are side by side, and each have a shape of 3. So we can apply a function to that whole array using map blocks with this lambda function. So this lambda function is just the square of the inputs, and you'll see that the result looks similar to the input array. And when you call compute on that, you'll get the result that you expect, which is just the square of every item of the array. So this is similar, this is equivalent to just calling a to the 2. And you can check that those are actually equivalent things by looking at the task graph. So the task graph here, you can see that you start with an a range, and then you apply a lambda to it. And for the a squared, for the plain a squared, this is the map blocks version. And then for the plain a squared version, you just start with an a range and then you do a power on it. So it's easy to understand how this works, but sometimes it can be a little confusing to set these kinds of operations up. So often it's good to start by writing a function that works on just one block, so just one chunk of the Dask array. So here's a function that takes in one block of the Dask array and returns that block minus the first item in the block. So we can test that function out. So now that we've defined the function, we can test it out on any block of the Dask array. So here we're testing it out on the first block, or the second block actually, It's the same if you test it on the first block. And you'll notice that I called compute on this. This is because this array is actually like, we say that the chunks of a Dask array are NumPy arrays, but they can really be anything that looks like a NumPy array. So in this case, it's actually a Dask array with Dask arrays in it, but we can easily get out of that nesting by calling that compute. So now that we've tested how the function works on one block, we can run it. We can use map blocks to apply the function to our whole array, and we'll do that and call compute. So you'll see that you get this repeating pattern. First, you get the result from the first block, then you get the result from the second block, and they get concatenated together into an array with the same shape as the input. So you can sort of explore your intuition with this by changing the chunk size of A. So here, if we rechunk it to have chunks of size 2, you'll see that we have 3 chunks, and you'll see that this little pattern repeats 3 times, because the output depends on the size of the chunks in this case. So you can use map blocks to combine several Dask arrays. The only requirement is that they have the same number of chunks. So these 2 arrays have different size. This one has size 1,000. This one has size 100. But they end up having the same number of chunks. So you can see in this display that the number of chunks in X is 10, the number of chunks in Y is 10. So we can use map blocks to combine these 2 arrays. So here we'll take we have a new function that takes the max of A, takes in A and B, 2 different arrays, takes the max of each of them, and returns an array, a NumPy array, with the results of those 2 operations. So the output array will have size 2. The output of the particular function will have size 2. So you can see that this pattern repeats itself. Like there's the max of the first chunk of A, the max of the first chunk of B, and so on. And the chunks argument here, James mentioned this a little, the idea that we're chunking, that we can set the size of the chunks. By setting this, we let Dask know what to expect from the output of this computation. So as when you look at the result, you can see that Dask knows that the output will have this, each chunk in the output will have size 2. This is often a really important thing to do when you're using map blocks, especially if you're changing the shape, because it allows you to chain together other operations with this result, and have the right shape and have them all work. So there's special arguments that you can pass into, that you can use in the functions that you then use in map blocks. Those special arguments are block ID and block info. They're similar in some ways, but it can be easier to think about. Block info has more complete information, but block ID can be simpler to think about. So I think I'll just start by showing what the output of this function is. So this is the same function as above, where we take in these X and Y arrays, and this time we calculate the max of each of them. And this time we're just added block ID equals none and block info equals none to the function definition. And for one of the blocks, we're going to print the block info. So you can see that this whole dictionary is what you get out from the block info. And there's a lot of really useful information in here. There's the array location, chunk location. So there's the of each of the input blocks. And then there's all that information also about the output block. So the thing that you're filling essentially. So the chunk location is the location within the chunk organization structure. And then the array location is the actual index of the actual values. So these keyword arguments are really useful when you're using map blocks to generate data. So this is an example where we're going to generate an empty array, which has a 10 by 10. Here, I'll just put this cell and show you what this empty array looks like. So it's an empty array that has 10 by 10 chunks. Each chunk is size 1, and we'll generate data and fill that array with generated data that takes the input index value and takes like the range essentially between that and the next one and the next value. So you can see that you get this output that has the same number of chunks, but each chunk has grown to be 10 by 20. And you can call .compute on that if you're interested in seeing what exactly we did there. So that example is a little contrived, but it can be a useful pattern to use when you're doing custom I/O operations, especially when your data is really big and you're going to be operating in a distributed context. So you can read files based on the chunk location or the array location, and sort of puzzle them together. So there's an exercise here, which is a tiny puzzle. So what you're going to, so it creates an image of a bicycle, and all of the pieces are contained in this puzzle directory. So since we haven't taken a break yet, I'm going to leave you here, and we're going to take a 10-minute break. And you're welcome to work on the puzzle, to hop in the chat and ask questions, and then we'll come back and continue on. So I'm going to leave you here with this exercise of trying to put together the puzzle piece from the chunks that are in this directory.
Awesome. Thanks, Julia. So yeah, let's everyone meet back here in 10 minutes.
So while we're waiting, I would like to let everyone know that if you have any questions, feel free to put them in the chat box, and either Julia or James will answer your questions.
All right, so that's been 10 minutes. I hope folks are coming back. Real quick, I'll share my screen real quick. I just wanted to briefly address one of the questions that was answered in, or was asked in the chat. Hopefully you can see the overview notebook that we looked at before. I kind of just blazed through the plotting part of this, like the diagnostic dashboards parts of this. I wanted to just talk about that for a quick second. Those diagnostic dashboards are only available on the distributed scheduler, so that we don't get those nice or not all the same nice diagnostics with the single machine schedulers. So when you create a distributed scheduler by, in this case, just creating a client object, there are a couple ways that you can look at all those plots. One is you'll notice there's this dashboard link right here. You can click that. That's one way. What that'll do is it'll open up this dashboard in a separate page for you. And this is nice. Like I'll do some computation and you'll see the stuff, the same things we saw before. If I import Dask array, because I've restarted my kernel, you'll see the same things happening over here. We'll see the task stream, all this nice, all these goodies, the bytes stored per worker, which is not a lot, albeit. So that's one way to view things. Oftentimes when you're working in JupyterLab, people like the experience of having those plots sort of embedded directly into JupyterLab. So to do that, you can go over to the Dask JupyterLab extension in this left-hand side. Here, click that. That'll open up this side here. You can click this magnifying glass. It's already attached to this cluster. The JupyterLab extension has already found the cluster I'm using. If it hasn't, these buttons will all be grayed out for you. You can click this magnifying glass. That will find the most recent client that you've created and attach to it. These buttons should then become orange. And then all the plots over here, each one of those has a corresponding button here. You can click the button, for instance, to look at the task stream, you can click the task stream button. That will bring up the task stream plot over here, and you can move it around as you see fit. You can also look at the graph, and you can move that around as you see fit. So just click the plots you'd like, and then you can get the same experience as looking at all these plots over here in a separate tab, all directly embedded into JupyterLab. So here you'll see this happening. This was a bad plot to choose because the schedule has too many tasks to display. So I will not show the graph plot. But hopefully that clarifies how to actually view the dashboard both inside and outside of JupyterLab. And with that, I'll hand it back over to Julia.
Cool, thank you. So I left you with this puzzle. The solution is here. If you click on the collapse cell, so you read in the block ID, you look for the index, you find the puzzle piece that matches that index, and then you can put them. Hopefully, you can put them all together. Maybe I messed something up here. Okay, I just didn't execute my cells in order. A classic problem. Okay, so similar to map blocks, Dask DataFrame has map partitions. So I'm just gonna do a quick example here. All the principles are the same. So you can pass a data frame. Here we have a data frame with 2 columns. two different D types, so integers and floats. And then you can apply this function which takes the data frame and an arbitrary threshold, and then sees if the sum of the columns is greater than the threshold. So we get the output is all a series of booleans. Internally, map partitions is used to implement lots of the methods that make the Dask data frame API look like Pandas. So this is the real implementation of dataframe.index, which just does a get adder on the name index, and then had a couple extra quarks, but it's really just using map partitions under the hood. So in this example above, you see that there's this meta argument. So I'm just going to take a little aside here and explain what meta is. So meta is, there's Dask data frames and Dask arrays have this special attribute that's called meta that stores the metadata about that array or data frame. So things like D type, column names, and order, the order of the columns, the name of the whole object, and the type. So Pandas data frame, QDF data frame, NumPy array, QPy array. That's all stored in this meta object. So it's kind of like the scaffolding that the Dask array or Dask data frame uses. So you can print the meta object on any Dask collection, or at least on arrays and data frames. And you'll see it's an empty Pandas data frame. So if you look at the type, it's actually a Pandas data frame. And it contains the information about the D type and all the other information that Pandas array with a Pandas data frame would have. So having this metadata lets Dask know what your array is going to look like, which allows Dask to do these pretty displays, where it knows, for instance, the D type of each of these columns. So the
question real quick, like that pretty display there, like I understand that like 3 and 4 are like the final indices of that data frame. I just have a hard time like figuring out like what that view is actually representing. It's like, index 0, it's going to tell me it's an int 64 and a float 64 for that column. But like the dots underneath it and like the 3, 4, that's the thing that was just confusing.
Yeah. So the actual values aren't known by Dask ahead of time, right? Because Dask just has this task graph that represents the data, but it doesn't know the data at all. So the dots represent that lack of knowledge. And the reason that there's this 3 and this 4 is because of the way that this array is divided up. So you can see if you look at the first partitions of this array, of this data frame, you'll see it goes from 0 to 3. So that's why this first, so each line in this represents one partition. So the second one goes from 3 to 4. So that's what it's trying to represent. But I do understand that like it can be weird to look at these things until you get used to them.
So that's basically 0 to 3, is the first partition, and then 3 to 4 is the second. If there was like a third partition to 7, let's say, there would just be a 7 down there.
Yeah, and you can see that that information is captured in this divisions attribute, which captures the boundaries of each of those partitions. So 0 to 3, 3 to 4. So that's what it's representing there.
Thanks.
So the point of having this meta is it has a couple of benefits. It gives Dask a sense of what the output will look like, which is what we just talked about. And also, when you add an item to a task graph, so when you chain together operations in Dask, Dask tries to run the function on the meta before you call compute. So when you construct the task graph, Dask runs the function on the meta. So this gives Dask a sense of what the output will look like, what shape it'll have and whatnot, what D types. And also if there's any fundamental issues with the function, Dask will fail right then rather than when you call compute. So that's a nice benefit. So this is just an example of the output, the like shape and the type of the output being known before Dask has actually done the computation on the real data. So we have a data frame that's now, because you called that sum, it's reduced the axis and it's become a series with the columns as the index. So it's sometimes when you're writing custom functions or other times in Dask, it's useful to provide the meta as a keyword argument. So here it's the same function we were talking about above, but we're passing the meta and saying that it's going to be a Boolean, which is shorthand for saying a series, a Pandas series with D-type Boolean. So you can see that it's actually slightly faster if you pass the meta object, because instead of having to compute that meta on the data frame, it just knows it ahead of time. So that's sometimes a good approach to take. So so far we've talked about map blocks and map partitions, which operate in each block in isolation. But it is they're not great for when you want to know when you need to know something about the other blocks in your array, or when you are changing the order of the blocks. So for those, you need different types of things. So you need map overlap is the approach that you'll take when you need to know something about the neighbors. So some examples of those are convolving a filter across an image, doing anything rolling, or taking a partial derivative. So here's the map overlap documentation, and here is an example of taking a derivative. So it's a very similar structure to the map blocks, but it just has these extra arguments of depth, boundary, and trim. And really depth is the one that is most essential, which is saying how many items are we going to take from the neighboring blocks. So you can take a look at this, and this graph is a little hard to separate out, but the most important part is to see that there's two columns, two towers of operations, which is a little mixing in between. So just the little neighbors are getting mixed together. I'm going to skip this example, but you're welcome to this exercise, but you're welcome to come back to it. It's about applying Gaussian filters and blockwise computations. So this blockwise computations are similar to map blocks, but the difference is that with using blockwise, you can change the order of your shapes. So this will look very familiar if you're used to like matrix operation stuff. So we have two arrays. We can apply a function, and we determine we set the order of our input chunks for both our arrays and the order of our output chunks. So you see that here you have an array with shape 2, 2, and then if you swap the order of your output chunks, you have an array with shape 4, 1, or 1, 4. So this is a diagram of what's going on, kind of. So we do the operation, but instead of putting the chunks, stacking them in the same order as the input, we put them in a different order. Internally, this is used to support transpose, and also map blocks itself is implemented using blockwise internally. So for transpose, for instance, we transpose each individual chunk, and then we transpose the chunks as well. Reduction, then the next two that I'm going to talk about are have to do with reducing the dimensionality of the output. So all the ones so far, you have roughly the same size of input as you have output, but reduction and aggregation, you're reducing that final output. This is a place that Dask can do. This is something that Dask can do really well, because especially in a distributed context, these type of operations work really well because you end up transferring less data because all the operations happen, the aggregation happens, and then only the final data needs to come back to the client. So internally, reduction is used to support a lot of the operations that reduce the dimensionality, like sum, mean, a lot of the other standard operations. So we'll just look at sum for a second here. So we have an array with a shape of 1,000 by 1,000, and we can visualize this sum. We can see that that takes a sum on each chunk, and then it takes a sum of the different, it takes a sum of the results from each of the chunks, and then it keeps doing that and stepping up. So really what I want you to take away from this is that you can control the way this task graph looks with this argument split every, which is very useful. So in this case, this is an example of using split every to say, I want to do the partial aggregation on every 2 chunks in the 0 axis and every 5 chunks in the 1 axis. So this is the same exact function, a.sum, but because you set split every differently, all of the sums actually come together at once and get aggregated. So you can have a lot of control over how your task graph looks just using these like a.sum, which is a top level, high level function, just by using split every and some of the other keyword arguments. So the last thing I'll touch on is group by aggregation. This is really for data frames, and it has to do with, it's similar to reductions, but it's for when you want to do a group by and then you want to apply a custom aggregation. So there's a lot of operations that are supported by default with group by, mean, max, all the regular ones. But sometimes you want to create a custom aggregation, and this is the best way to do it rather than using apply. Apply essentially shuffles all the data so that a whole group is in one partition. But if you use a custom aggregation, it just takes each chunk, groups the chunk, but leaves it as one, and then applies a function, and then you get the output. So this is what it would look like to write a custom aggregation for mean. So on each chunk, so the first function is the function that will happen on one particular chunk. Then the next function is what will happen on the results from several chunks. And then the last function is what will happen on all of those results. So if you look back at this graph here, the first function is what happens on each chunk. And then the second function happens on aggregations of those chunks. And then the last one is like the finalizer that gives you the real output. So you can see this is equivalent to just calling df.groupby name.mean. So it's the same thing. We've just created our own custom version of that function. You can look at the task graphs to compare what they look like. You can also try running this if you want. It's very, very slow using apply. So often custom aggregations is a better method. So these, I've thrown a lot of different methods at you guys, but essentially, like, you can use map blocks and map partitions when the chunk location of the input matches the chunk location of the output, and you don't need, and the function is fully parallelizable. You don't need to know anything from other chunks. Map overlap is for when you do need to know things from other chunks. Blockwise is for when you want to move your chunks around. Reductions are for when you're reducing the dimensionality, and group by is for when you have a group by. So with that, I'm going to move on to talking about graph optimizations. So it'll be the next notebook.
I might cut in for a second. Julia, just real quick, we did not talk about this beforehand. Do we want to maybe, for time's sake, drop the custom collections notebook so that we can sort of more take our time in the optimizations? Okay, great. So for everyone, we're going to drop notebook, what is that? Number 4, custom operations. That's still around if you would like to go through it at another time, but just so we don't have to totally rush through this next notebook. Yeah,
that's a great idea. Thank you, James. Yeah, so custom collections is here. You're welcome to look through it later and ask us questions. But yeah, let's take our time with graph optimizations. So graph optimizations are one of the great reasons why one of the reasons why task graphs are like so great, because they allow us to optimize the task graph before we do computation. So what the goal of that is to simplify, the goal of optimization is to simplify computation and improve parallelism. So we can simplify computation by removing unnecessary tasks. So normally that's with this function called cull. And we can improve parallelism by reducing intertask communication, by fusing together tasks, or by inlining cheap operations. So replacing some operations with other ones, or replacing keys with tasks. So there's several different, all of these like fuse, cull, inline are all contained in this Dask optimization module, and they happen by default on Dask collections like Dask array, Dask bag, Dask data frame. But you can also write your own Dask optimizations. And that's really what we're going to be talking about in this notebook, like how they work and how you can go about writing your own, so that you can create your own tasks, your own optimization. So this is the same example that's in the documentation, but we're just going to be sort of talking through it to deepen our understanding of optimizations. So we're going to be just talking about task graphs in this case, not collections, but we'll talk about how this all relates to collections at the end of the notebook. So in this example, we're going to be counting the frequency of the words orange, apple, and pear in a list of words. And then we're going to be formatting an output string and printing and returning. So here we have a function for formatting, here we have printing and returning, and here we have our input words. So we can run this cell to get this first task graph. So I'm going to actually pop this into a separate side view so we can look at it as we go along. And we can see how we're improving the task graph. So this is our original one that we just created. So you can see the inputs, value 1, value 2, value 3. Those are the actual fruits, and then all the words, and then we have this first operation, which is the counts, and then we have the formatting, and then we have the printing. So we're going to talk about how we can clean up this task graph, make it simpler and more parallelizable.
How did you do that Jupyter magic?
Oh yeah, it's I right-clicked and then create new view for output.
Create new view. Oh, okay. I was clicking on the output. Oh yeah, that's there too. Okay, got it. Okay.
Yeah. So then you can drag it on side and keep it there while you run. Okay. So the first one we're going to look at is cull. So cull takes, so we're going to say, instead of caring about all of the print 1, print 2, and print 3, we only care about print 1 and print 2. Those are the only outputs we're going to care about. So how can we cut parts out of this graph to make it simpler, given that additional context? So we take the cull function and we pass the task graph and these this list of the outputs that we care about. And then you can see that what you end up with is you've completely eliminated this whole print 3 tower of operation, and you just have print 1 and print 2. So that is cull is a default optimization that happens on most collections, and it helps simplify the whole graph and makes it easier to serialize, and it just makes it simpler. In practice, one of the examples is in data frames, when you select a particular, so here we're creating a time series using a demo data, and we can put it in a Parquet file, and then you can see that if you read it in, every particular file in that Parquet directory, which represents, each file represents one day, and each of those is a separate task. The reading of each of those is a separate task. But when you pull just one day, then you optimize it, then you see that call happening where instead of reading each of these files, it only has to read the one. So the task graph goes just from selecting this one day, the task graph goes from 30 inputs to just one, to 30 tasks to just one task. So back to our example about the fruit words. So another type of optimization that you can do is inline, which it can improve the efficiency when there's just little functions that little functions or little constants that are being assigned to the task graph, but they're very simple. So in this case, instead of passing value 1, value 2 as inputs, we can just print them out. So I'm actually going to look at this as a graph, as a dict, because I think that makes maybe more sense. So you can see that we've inlined here the function. We've inlined the inputs to the format instead of using these. Instead of using the keys in the task graph, we're just inlining the word orange right into the task graph. You can do the same thing with functions, where if a function is really straightforward, instead of assigning it to a task in the task graph, you can just inline the whole function. So you can see that our task graph is getting much simpler, and without losing, like, it still does the same thing though, right? It's not losing any of the actual logic of it. The last one that's very common is the fuse function. This one's really good, especially for distributed context, because it makes it easier to serialize because it reduces the number of tasks, and then it makes sure that all the tasks can go to one. It makes it easier for tasks to go to one particular worker rather than moving around. So here we fuse together the format and the count into one into one operation, into one task. So to put it all together, you can do the call, inline functions, fuse, and you get the output. So these are like the standard ways that you can optimize, that Dask optimizes its task graphs by default. You can also write your own functions that take in a Dask as a task graph as a dictionary and a list of keys, and return a new Dask dictionary task graph. So, and then you can set those to operate on your different collections. So on Dask array, for instance, using the Dask config. So you can set this. So for example, here we're setting a new array function, and then you call Dask compute. It uses that optimize that you have defined. And this is an example. This is an exercise that I guess I'll let you do. Finally, let you do an exercise, which is if it follows this. There's this package called GraphChain that implements custom optimization function that caches data if it's already been computed. So this is a task graph that I pulled from their README, which is to create a data. It creates a data frame. There's a function to create a data frame. There's some like complicated computation, and then there's a summarize step. So this is the little task graph that represents that, where you have a create data frame, complicated computation on the results of those, and then summarize. And you'll see if you look at this that create data frame with this same exact arguments appears twice. So the goal of this exercise is to only do that operation once. So it's kind of like the opposite of inline, where instead of replacing a key with a task, we're going to be replacing, we're going to replace one of these values in this dictionary with one of these keys that appears. So there's a little scaffold for how you might set this up. And I'll let you work on that. And we'll reconvene in another 10 minutes. But I'll be here if you want to ask any questions or get advice on this.
Sounds good. Thanks, Julia. All right, so we are about a minute left in our exercise / break time. Just wanted to open up the floor. Are there any questions at this point that we should, that you may have, or are we good to jump back into things? Drew, you've had a bunch of good Jupyter Lab related questions, which has been nice. I also didn't know how to pull that thing out, the output into a separate tab. I will use that in the future.
I use a lot of Jupyter Lab and I don't know any of the tricks. So what am I going to do?
Yes, I use a lot of Jupyter Lab poorly.
Yeah, exactly.
Yep. Cool. Okay, well, if there are no questions now, it's totally fine. If you think of any other ones, feel free to paste them in the chat. I'll get to them while Julie is talking and vice versa. And if there aren't any questions now, maybe Julie, do you want to pick things back up?
Yeah, sure. So this is the end of the notebook actually. So this is the solution if you've been working on this exercise. So just to summarize, like there's these several different optimizations that are included by default, but you can always write your own and you can add them to existing collections using this config approach that we show here, or you can, if you're writing your own custom collection, which we're not going to get into this tutorial, but there's the notebook if you want to explore that, then you can write a Dask optimize method. And they'll always look like these optimize function, like the optimize function that we wrote in the exercise. So yeah, I'll hand it to you, James, to talk about schedulers.
Yeah, great. Thanks, Julie. All right, let me share my screen. Hopefully you are seeing a Jupyter Lab session right now and not the shame that is my email inbox. Okay, so let's move over to the 5th notebook now, distributed scheduler. Okay, so thanks, Julia, for the custom collections topics. It's great to see sort of the advanced methods we have available for custom operations and also sort of graph optimizations to help make our graphs more efficient. So appreciate that. Here we're kind of switching gears away from graph optimizations over to talking more about the scheduler again, the thing that actually computes the task graphs. So in this notebook, we're specifically going to talk about the distributed scheduler. We sort of glossed over a lot of things in the overview notebook, and we're going to maybe zoom in a little bit more on different components here. Talk about the different parts of the distributed scheduler, also talk about how to inspect the internal state of the cluster, the schedule of the workers, things like that, and then how to use Dask's plugin system to extend some of the functionality of your clusters. So let's start with this Dask distributed cluster overview first. So let me see if I can actually make this a little. Oh, no, that's fine. This can fit. So there are a few main components of any Dask distributed cluster. There's the scheduler, the workers, and the clients. So here's this little diagram here. So there is a single centralized scheduler shown here in blue, and this sort of keeps track of everything. So you are submitting tasks to the schedulers, and that could be using client.submit, like just run this function. It could also be, I have some big array computation that I've set up and you call compute on it, and all of the tasks for that array will get sent to the scheduler. The scheduler tracks a ton of state. It computes all the dependencies, various priorities of tasks. If you have any worker restrictions or things like that, like maybe you want some of your tasks to only run on GPUs, for instance, you can tell Dask to do that, and the scheduler will remember and keep track of this task. I'm only going to assign it to GPU workers, for example. So yeah, the scheduler keeps track of all that state. It will also, it's in sort of constant communication with the workers, which are shown down here in orange. This diagram just has 3 workers for sort of simplicity, but you can have thousands of workers if you'd like. Or just 3, that also works. So the scheduler will take these tasks that you have asked it to compute, and it will send them off to the workers. The workers will then do their computations. We'll talk a little bit about that in a second. The worker will compute these tasks, compute these Python functions for you, and then hold on to the result. The workers and scheduler are constantly communicating with one another. when certain events happen, like the scheduler will say, hey worker, I have a task that I want you to compute, and it'll send a message from the scheduler to the worker. The worker will say, thanks scheduler, I'll start on that. It'll tell the scheduler that that task is currently being processed, and eventually the computation will happen on the worker, and it will have its result. You will say, I wanted you to run this NumPy mean function on this NumPy array. I now have like the mean of that NumPy array stored in my memory on the worker. It'll then send a message back to the scheduler saying, hey scheduler, I've finished this task. So whenever and I have the result in memory. So if there are other workers that are computing other tasks that rely on this, you can tell them, I have the result. They can ask me for the result of that if there are any dependencies. And whenever the client, in this case, like the user, asks for the result for this task, come to me and I will give it to you. So these are all the various types of like messages that are sent back and forth between the scheduler and the workers. So those are sort of the two foundational components. There's also the client process itself. And the client process is sort of the user-facing entry point to the cluster. So the client process lives wherever you are. That could be in a Python script somewhere where you're using Dask. That could be like in the tutorial, like here, we're in some Jupyter Lab notebook. We will create a client process here in the Jupyter session. And you use the client to submit tasks. Like I said before, like you can do that explicitly by saying, client.submit, here's the task I want you to compute, or by calling some other compute method on like a Dask collection. So those are sort of the main components of a distributed cluster. I want to just have a couple additional comments about the workers themselves, which are down here, so I can remind myself. Each worker here, so like I'm showing these each component here as kind of its own square or its own box here. You can think of each of these as running in its own process. So you're creating a new client object here. You're creating like a scheduler process here that could be locally on your own machine. That could be on some remote machine as well, running on AWS or something like that you are communicating with. Same with the workers. The workers can also be all of these can be happening locally on your own machine by spinning up local processes, or these could be processes on other machines. The workers here are a little more misleading. So, or rather, like this diagram isn't capturing the full information. So each worker is its own Python process, but within each of those worker processes, each worker has its own concurrent futures thread pool executor. And that's where the tasks actually get computed. So each worker, you spin up a worker process, that process actually launches its own thread pool, and that's where the computations happen. So just like in the single machine schedulers, where there's this trade-off between processes versus threads in the multi-processing and multi-threading schedulers, the same, like all those same details apply to the distributed scheduler as well. By default, like if you don't specify anything, that thread pool, it'll do something similar to what the single machine schedulers do. It'll kind of inspect the number of cores that are on the machine where the worker is living, and it'll create a thread pool that corresponds with the number of cores. You can also, if you want, you can say, hey, I want this worker to have 5 threads, like explicitly, instead of doing this auto detection thing. So that's one subtlety with the workers. Another subtlety is that there's actually, like, this diagram is actually missing something. I'm saying the 3 parts of the cluster are the client, the scheduler, and the workers. There's one other piece there, which is actually the nanny, which is not often discussed. So, and it's actually like the default behavior of Dask. So you can always turn off the nanny, and actually we'll do that later in this notebook. We'll say, don't use a nanny, but by default, we have them. And what that is whenever these worker processes are spawned, and we'll talk about how you can create worker processes in a couple cells down. By default, there's actually a separate nanny process that actually launches the worker for you. So there's this external process that's actually monitoring the worker. And that's useful for a couple of reasons. One is that it allows the nanny process can actually restart the worker process. So there's on the client, there's a client.restart method. Oftentimes this is used if your cluster gets into like a, let's say, bad state. You can call client.restart. It'll just kind of flush everything and restart your cluster altogether. That's only possible if you have some like external thing that can actually close down the existing worker and restart that worker. That thing here in Dask is the nanny process. It also lets you do some additional monitoring that are sort of all around, like restarting the worker. So for instance, if the memory on your worker starts to blow up, we have certain thresholds that are set where the nanny will say, I'm actually forgetting what the default value is off the top of my head. Let's say it's 90%. After the worker's memory has reached like 90% of its memory limit, the nanny can actually restart that worker altogether. So that's the other kind of missing piece here, is this additional nanny process to monitor the workers. That's the default behavior, but you can also opt out of it if you'd like.
Is there just one nanny process
yeah, great question.
For all the workers, or is there one per?
There's one per worker. Great question. Yeah, so each nanny, there's a one nanny to one worker mapping. Okay, so those are like the basic components of the cluster: client, scheduler, workers, hidden state of the nanny. And that's sort of, hopefully we have a good sense of the players involved here and kind of what each of the players does. The next thing I wanted to talk about, oh, and here's some related documentation. In particular, I recommend checking out the journey of a task. It kind of walks through the process of like, I'm a user and a client and I submit a task. What happens from there? It kind of walks through each of the steps individually. The next thing I wanted to talk about was deploying Dask clusters. So deploying a Dask cluster involves standing up basically all the processes in this figure. Launching a client, launching the scheduler, launching workers. And there's a variety of different ways that you can go about doing that. One common way we see that people do that is by using Dask's command line interface. So when you install Dask and when you install distributed, you get this command line interface that has a Dask scheduler and Dask worker command line options or command line utilities. So like, say you have access to some big machine somewhere and you want to like launch a Dask cluster on that. One way you can do that is to like, let's pretend you SSH into that machine, and like, then in that machine, you would use the Dask scheduler command line utility. That will actually launch this scheduler process for you. And it'll tell you the address for where it is. It'll say, I'm a scheduler and I'm at this location. You can then open up several other like tmux sessions, SSH into that machine, and launch a bunch of workers. To launch a worker, what you do is you use the Dask worker command and you point it at the scheduler. Keep in mind, the scheduler and the workers all are constantly communicating with one another. So when you launch a worker process, you have to tell it where the scheduler is to connect to. So you just say Dask worker, here's your scheduler. Dask worker, here's your scheduler. Dask worker, here's your scheduler. And that'll launch three of these three worker processes. You can kind of rinse and repeat this process as many times as you like for as many workers as you want. This is sort of a really low level kind of manual logging onto a box, launching a scheduler, launching a worker processes. This is one way that you could launch Dask workers. Another way, which is not advised to use actually, or rather like this is not the first thing you should try when launching Dask workers, hence the warning sign, is you can actually use Dask's Python API directly to launch worker and scheduler processes. So you can, from Dask.distributed, import the scheduler class, the worker class, the client class, and you can launch those processes. So for instance, here, these are one reason they're not actually, these are typically used in very rare cases, important cases, but rare ones. So oftentimes the last way to launch clusters is actually what we'll recommend. But this is useful. Oftentimes when people see like a scheduler object and a worker object in Python, that fits well with people's head with, oh, here's me creating a scheduler process. Here's me creating a worker process. So to create a scheduler, you can just instantiate a scheduler object. Notice that there's async here. That's another reason we don't always recommend using this as the way to deploy Dask clusters, is because there's other like async await code that some users aren't necessarily comfortable with. So you can instantiate a scheduler object like this, much like in the command line interface where you have to say Dask worker, here's your scheduler. You do the same thing in Python. You say create a worker, and here's this scheduler object has an address. You can say, here's your scheduler address. So here's how I create one worker and it connects to that scheduler. You can like have as many async with workers as you want. Like each one of those will create its own worker process. And then at the end, you can create a client. Notice I'm putting asynchronous equals true here. That's another oddity associated with, not oddity, but another advanced feature of using the Python API. And then you can do all your normal things. You can use client.submit to submit some function to this cluster. So I'll go ahead and run that here, and we see a bunch of log messages getting printed out. This was like when I created my scheduler, here it is. Here's when I created my workers. And you can see at the end, I am printing out the result. I'm just summing up range 100. The result happens to be 4,950 here. So this is another way one can launch a Dask cluster. Like I said, not recommended. This is more just kind of or not recommended for everyday use. This is more just illustrative. This may fit your brain a little bit, thinking about launching scheduler processes with creating Python objects or instantiating Python classes. The last way I wanted to talk about launching clusters is actually the common case. Dask has the notion of like a cluster object. And there's a variety of different flavors of cluster objects, but they all implement the same cluster API. So Dask has a built-in cluster manager called local cluster. And what this will do is we'll launch that scheduler and worker processes all on your local machine. So this doesn't require any setup. This is just launching local threads and local processes on my machine here. You can tell it how many workers you want it to create and how many threads per worker you would like to have. This is like the size of the thread pool on each of the workers. You can also, these are totally optional. You can also just do local cluster parentheses, and that's totally fine. It will see how many cores you have, create a certain number of workers and threads per worker in accordance with that. But here's how you create a cluster. And what that just did was spun up a single scheduler. And as you can see, 4 workers, each of them have 2 threads. So I have 8 threads altogether. Here's the dashboard you can link to if you want to get the corresponding diagnostics for that particular scheduler that I just launched. So this is really how most people deploy Dask clusters. They will instantiate some kind of cluster object, some kind of cluster manager. And that cluster manager will handle everything behind the scenes for you. In this case, it's spinning up local threads and processes. We'll see examples of when we're not doing local things right here. So the cluster API has some methods that are applied to, that are sort of hardware independent and apply to wherever you happen to be running your cluster. So for instance, I spun up 4 workers here. The cluster API has a scale method. So I can use that to scale to 10 workers here. And so you'll see here, it's launching up some other things, and oh no, that's unfortunate. Address is already in use. Let me go ahead and clear my kernel. I might have some other clusters running elsewhere. Let's try this again. Okay, scaled up to 10 workers. So you can see I started with 4 and it's scaled up to 10 workers here. I can also scale down to 2 workers. If I want more workers, you can ask for them. If you want less workers, you can ask for them. That's scaled down to 2 workers over here. You can get logs for your clusters. So for instance, here there's a little drop down. You can see I can get the logs for my scheduler. These look exactly the same as what we had above when I was creating my scheduler in Python here. So here's all the logs from my scheduler. You can see me creating workers and then attaching to the scheduler. Here's the logs for one of my workers. Here's the log for my other worker. We can also shut down the cluster. So it's not a big deal here because I'm using local threads and processes, but if I'm running on something on GCP, I'll want to close down those workers so that if I'm not doing work, I'm not paying for those workers as well. For those computing resources. So this cluster manager API is the typical way people will deploy Dask clusters. Throughout the rest of the tutorial, we're just going to use this local cluster here. It's the easiest thing to spin up, but everything we're going to talk about applies equally to any other kind of cluster you might deploy. Speaking of deploying other clusters, there are a variety of other cluster manager objects in addition to the built-in local cluster, which you can use for a variety of different hardware, the various hardware you may have access to. So for instance, if you would like to deploy your scheduler and workers on a Kubernetes cluster that you have access to, you can use the Dask Kubernetes cluster manager. If you have an AWS account or your company is using Azure or GCP, you can launch a Dask cluster there using Dask Cloud Provider. Same for Yarn clusters, MPI environments. If you have an HPC job queuing system like HD Condor or PBS or Slurm, you can use Dask Job Queue to launch a cluster on those systems. And sort of the setup looks pretty similar for across all the cluster managers here. So for instance, in Dask Kubernetes, if you wanted to launch a cluster on Kubernetes, you would install Dask Kubernetes, import this kube cluster object. So like use kube cluster basically instead of local clusters. The ... here represents other like backend or like hardware specific things. So you can go check out the Dask Kubernetes documentation. Like one of those inputs is probably like maybe a kube config file, maybe the Docker image you want to use for your workers, or the Docker image you want to use for your scheduler. Same thing here. If you were if you wanted to launch a Dask cluster on AWS, you could use the Fargate cluster from Dask Cloud Provider. Again, ... would be AWS specific things. You may have to pass in an AWS IAM role, or you'll also have to say the Docker images you want to use, things like that. So the actual setup here is relatively uniform across the projects. There's going to be like hardware specific keyword arguments, but the name of the game is basically create one of these cluster objects. Now you have spun up your cluster on the corresponding hardware. Now you can do your Dask workflows on it.
If you had like an EKS, cluster, which is, technically a cloud provider thing, would I use like kube cluster for that, or would I use like from AWS import like, I don't know, kube cluster or something like that?
Yeah, it's a great question. For that, I would actually recommend Dask Kubernetes. Yep, because
okay,
you already have the Kubernetes cluster up and running, so it will take care of that for you.
Okay. So part of the quarks there will be like things that are needed for AWS to talk to that EKS cluster or something.
Yeah.
Okay, cool.
Yep. Exactly. So yeah, just disclaimer, Julie and I work for these companies, but I do want to say there are also companies. So everything I've linked to here is a totally community open source project within the Dask ecosystem. So I'm putting on my company hat. I am going to say that there are companies out there like Coiled, who I work for, and Saturn Cloud, who Julia works for, who do offer Dask as a deployment services. So that's all I wanted to say. I've linked here. I'm now taking off the company hat and putting back on the free and open source hat. Okay, great. So that's all about like deploying Dask clusters. So like I said, for the rest of this tutorial, we're just going to use the local cluster because that's the easiest thing to kind of get up and running with. So the next thing I want to do is talk about inspecting the state of the cluster, actually figuring out what's going on in the cluster. So as we've already said, we have these nice diagnostic dashboards and performance. We haven't said this yet, but there are performance reports too. So that often is actually completely sufficient for many needs to understand what's going on in the cluster. What is the memory that's being consumed by my workers? How many tasks are currently running? What tasks are running on which workers? Oftentimes that like the dashboard is totally sufficient. I just want to say that before we dive in a little deeper, when it can also be useful to know how to dive in a little deeper. But I just want to say that up top, that oftentimes the dashboard is sufficient. So here,
James, there's another question in the chat, sorry, about authentication. So the question is, does the cloud provider set up auth between the client schedulers and the workers?
Yeah, that's a great question. I'm kind of going to just completely dodge it though and say, check out the corresponding documentation for AWS for Dask Cloud Provider.
Yeah, sounds good.
I think you come to Dask Cloud Provider and say, here's the VPC subnet I'm using, for instance, on my cluster. And Dask Cloud Provider actually doesn't handle that for you, is what I think is the case. But I would check the documentation just to be totally clear. So I'm going to punt on that one for now.
Yeah.
But that is a great question. Great. So here, we're going to spin up a local cluster. Earlier, I said you can opt out of the nanny using that nanny process if you'd like. Here's how you do that. Normally, you would just specify a local cluster like this. It would spin up things. Those workers will be the default workers that have the nanny. You can tell Dask to, when you're spinning up workers, don't use the nanny process. Instead, just use the old-fashioned worker process here. So the nanny, remember, just spins up one of these workers and sort of monitors it. The only reason I'm doing this here is because in a few cells, we're going to start inspecting and looking at the attributes on the worker. And the only reason I'm saying use the worker class here instead of the nanny is because later on, I don't want to be looking at the nanny class. I want to be looking at the worker class. So that's just kind of a quick aside. So here I'm going to spin up a local cluster and create a client, attach a client to that cluster. So I'll pull up, I'll go over here and pull up the, where is it, task streams and things like that. I always forget the ordering here. Task stream, great. So here's the task stream. I also like to oftentimes look at the progress. Great. So I'll run some computation here. So we can see all of our tasks flying around. This is great. This is often sufficient. There are a lot of other plots over here that I'm not showing, like the current CPU load on the workers. If you're using GPUs, the current GPU memory that's being taken up. There's a plot of the current load on the scheduler. You can see the CPU and memory usage of the scheduler sort of in real time. So you can see if your scheduler is like pegged, at 100%, for instance, that would show up here in this plot. So this is often totally sufficient for understanding what's going on in your cluster. One thing I did want to point out is Dask also has the concept of a performance report. So to use it, you just import it and then use it as a context manager. And what this does is actually takes a lot of these diagnostic plots and saves them to a static HTML file, which is super useful because now you have some artifact that you can look at later when a week from now you're like, oh, I was running something and totally forgot about its performance, or I just ran something and this was awesome and I want to share that with my colleague. You can save this file. It'll save a lot of the diagnostic plots and you can then send that off to someone else. So for instance, I just saved this performance report. You can give it a file name. It has some default value, but I named it myreport.html. I'll go over here and look at the files on my local system. There's that performance report that was just created. I'll go ahead and open that up. And this is what a performance report looks like. I'll make the text a little bit bigger. So it tells you how long the total computation took. It tells you the number of tasks and like compute time, the amount of time you spent transferring dependencies. It tells you information about your cluster, for instance, how many workers you have, the total number of threads throughout the cluster, the memory of the cluster, what Dask and distributed version you're using. It also even captures the code that you're running that produced the performance report, and we'll generate that down here too. So we can see this was the code that was actually running for this computation. And then each of these tabs is corresponds to one of those diagnostic plots. So I can see here's the task stream for that computation. Here is the worker profile for that computation. There's two. There's like the compute and the administrative. There are worker profiles for that are saved here to the performance report. So just wanted to point this out. This is a super useful tool for capturing and like making these plots persistent, basically. Okay, that being said, let's now dive a little bit deeper when you do need to go deeper, when what's shown in the performance reports isn't enough. So here I'm going to start submitting some tasks to the cluster just so we have some tasks lying around. So for instance, here is a double function which I'm randomly, so it takes some input and then I'm randomly going to raise a value error. And if I don't raise a value error, I'll return 2 times the input. This is just to kind of simulate, oh, I have some tasks which like are randomly failing sometimes, like something bad is going on here. So I'm going to submit this task with this double function with a bunch of inputs that will then create a bunch of, that'll send a bunch of tasks to my workers or to the scheduler, which then get farmed out to the workers. And we'll see some of the time those workers are saying, hey, a computation failed here. And it gives you some information like the function I was running was double. The inputs were, in this case, 31, 32, 43, 49. Like some of these inputs randomly failed and it let us know. Those are actually you can see those in the dashboard here by like the black tasks. Any task that's black in the dashboard means that task failed, just as a heads up.
Now,
so
what are the odds that the args are the exact same on my run and your run? Is there something?
Probably pretty high because I set the random.
Oh, okay, there it is. Okay, I was like, what the flip? Okay, got it. I see it. Okay.
I'm glad to hear that.
That seemed like magic to me, and so yeah, that's good.
Yeah. Some other things will be different later on, but that should hopefully be the same. So one nice thing about the local cluster is it gives us access to the scheduler object itself. So if I have my local cluster object here, it has a scheduler attribute, which I can now inspect my actual scheduler directly. I do want to note that this is often not the case. Like this is pretty much only the case with the local cluster. With many of the other ways you might deploy a Dask cluster, like for instance on AWS or some Kubernetes clusters somewhere, the scheduler is actually on a different machine. It's not where you are in your Jupyter notebook. The scheduler is actually on some remote machine somewhere else. So you don't actually have direct access to that scheduler object. We still can inspect it in a very similar way. We'll kind of circle back to that in a couple cells later down. But I do just want to note that like this is one of the niceties of the local cluster. It gives us direct access because everything's running on the same machine. We can get that scheduler Python object. So here is that scheduler Python object. It has 4 workers, 8 threads. So far, it has run. It knows about 50 tasks. Those are the 50 tasks right here that I've submitted. And the scheduler holds on to lots of state. So like I said before, it is sort of the centralized state machine for the cluster. The workers also have their own state machine, but they're less complex than the scheduler itself. So the scheduler has lots of information stored in it. Let's like look at this scheduler instance and to get a sense for what is stored on it. So the scheduler has an address that just is telling us the location. It's on localhost because I'm using a local cluster. If this was running on ECS, you would see ECS stuff in the URL here. It also keeps track of the time it started. This is like time.time run on the scheduler whenever the scheduler process started up. It also keeps track or keeps information about all the workers. So here we can see this is a dictionary. Scheduler.workers is a dictionary. The keys in that dictionary are like the addresses of all my workers, and the values are the corresponding worker state classes. Basically, the scheduler keeps around a class for each worker, and we'll look at those in just a second, but that has a lot of information about the worker. And as the worker and the scheduler communicate with one another, this class gets updated. So what we'll do here is this is a dictionary. I'll just go ahead and take schedule.workers, take the values to get those worker states, and just pluck off the first one real quick. So this is like one of those worker state objects. It happens to be this worker state object here. So this is not the worker itself. This is like the schedulers keeping track of the worker process. We'll look at the workers themselves in a little bit. But what does the scheduler state keep track of? Well, the worker state has an address here. It's also running on localhost. That's the address of my worker. That's unfortunate. Let me maybe restart. I think I'm getting some weird warning here. Sorry about that. Let's do this. Hopefully, because I'm setting the random seed, those are all the same. Perfect. Great. So there's the address. The worker also has a status. It's currently running. It could also be closed if you've already like closed down your workers. In threads, this is the size of that executor pool that's on the workers. It also keeps track of it keeps a dictionary of all the executing tasks and how long they've been running, all the currently executing tasks. So right now I've submitted my double tasks and those have either failed or have been completed. So it's not currently executing any new tasks. So this actually happens to be empty right now. The worker state also keeps track of like various metrics that the worker sends back. The worker constantly has a heartbeat with the scheduler. So all the workers are periodically sending messages saying, here's my state, here's my state, here's my state, with these various things. So number of current tasks in memory, the number of things I'm currently executing, along with some other stuff, the current CPU and memory load, things like that. It also keeps track of last seen. So like the last message, every time the worker sends a message, it also sends like, the scheduler keeps track of when it received that message from the worker. And it'll keep track of that in this last scene. So this is like the last time the scheduler saw the worker. So you can tell if a worker doesn't communicate for a while, you can see the last scene will get like farther and farther away from the current time. Here we're sort of going to loop over and look at what the the worker state last scene is, and then we'll sleep for a second and we'll do that again. And we can see that the last scene's attribute keeps updating by about a second. So we can see that this is constantly getting updated as the workers and schedulers communicate with one another. In addition to keeping track of all of the workers, the scheduler also keeps track of all the tasks. So here, I'll move this to the side real quick. Here we can see each of those double functions that got submitted has an entry here. We can see the key for the corresponding task. This is like a unique identifier for one of those task that you submitted, and a corresponding task state. The task state is kind of similar to the worker state, but it represents the tasks and themselves. So I can, in a similar way, pluck off the first task state object here. We can see it happens to be one that's in memory. Like here's an errored task. So this is one of those tasks that had one of those random failures. Task states also have a ton of state in them. You can see the key for the task. We can see what state it's in. So right now, this one's in memory. It could be error. It could be processing. It could be waiting, like it's ready to be computed, but hasn't started being computed yet. We can see the set of workers who have this task and result, have this task in their memory. Right now, only a single worker has this task in memory. If we had requested this to be computed on multiple workers, then there would be multiple worker state objects in this set. If the task has already been computed, we'll know how big it is, the number of bytes it takes in memory, what its type is, in this case, just an integer, and there's lots of data. You can tell Dask to repeat computations if they fail a certain number of times. By default, it doesn't do that. So you can see the number of retries that are allowed for this task are 0. Okay, that brings us to the next exercise here, which let's spend the next maybe 5 minutes doing. Let's try and answer the 2 questions over the next 5 minutes by just kind of going through and exploring the scheduler class and the worker state class and task state classes. The first question is, what are the keys for the tasks which failed? And of those double tasks, what are the keys for the ones that randomly failed? And how many tasks successfully ran on each of the workers? So let's maybe take 5 minutes real quick and work on those. Keep in mind the little ... here have some solutions for those. All right, it's been about 5 minutes. Hopefully you can see my screen again. So yeah, let's go over a couple possible solutions for this. So what are the keys for the tasks which failed? Oh man, unfortunately, I'm getting this thing again. Let me restart my kernel. This is the part that actually might be different for the different the random seed might not save us. Okay, great. So what are the tasks which failed? So one thing you can do is look at the scheduler.tasks. Remember, that's a dictionary that has like the keys and the task states. And what you can do is you can get all of the keys for the tasks who have a state of errored. So you can do that, and it looks like that. These are the individual keys for the tasks which failed. How many tasks ran successfully on each worker? There are several ways you can do this. So I actually have two solutions here. One is commented out. Sort of the brute force way is to, so here I import default dict. I first get all the errored tasks, all the tasks which didn't run successfully. I then create a default dict with integers, and I loop over all the tasks. And I say, if the key is in the errored tasks, because I'm looking for the ones that ran successfully. So if the key is in the error tasks, just continue. Like, don't worry about it. Else, if it's did run successfully, then loop over the scheduler.who has key. This tells you all the workers which have this key in their memory, and add one to the like counter dictionary. So what that does is returns a dictionary with all the worker addresses and the corresponding successful tasks which were computed. Another way to do this, which I've commented out here, is to, if you'll remember the worker state metrics, one of the things that the worker constantly tells the scheduler is how many tasks that it has in its memory. So you can also just loop over all of the workers to get the worker states, look in the metrics, and look at the in-memory key here. That's another way. It'll give you the same answer. Different order because of ordering here, but other than that, the answer is the same. Okay, so that's for those two exercises. The last thing I wanted to look at was, like, so far we've actually just looked at the scheduler. We can also look at the workers. I'm actually going to go through this pretty quickly because the story is kind of the same. This is why I chose to make that worker class worker instead of having it be the nanny by default, because then these would all be nannies on the local cluster. And those just don't have all the same rich state that the workers have. So here you can pluck off one of the worker classes, the first worker class, and look at what the worker has. Kind of the same story as the scheduler, like it has an address. It has the number of tasks which are currently executing, the number of tasks, a cumulative run of the number of tasks it's executed throughout the course of the worker's lifetime, the number of threads in the thread pool, the actual thread pool itself, or the thread pool executor. This is where the tasks are actually run. The keys which the worker currently has in memory. And then, like, there's this data attribute. This is some mapping. It's a crazy buffer RLU thing because it supports like spilling things to disk basically. So, but we can, like, it still is a mutable mapping interface. We can loop through it, giving all the keys, and we get the corresponding values. So here are all the tasks it has in memory, the keys, and here are all the values for those tasks. Those are all the results that it has that it can serve to other tasks and things like that. So yeah, just kind of quickly getting over that. So in the sake of time, I'm going to move on to the last two things. I said earlier that there oftentimes you actually don't have direct access to the scheduler and workers directly because those happen to be on remote machines. You just have access locally to your client, which connects to the scheduler. However, Dask does have a couple of methods that we can use to talk directly to the scheduler and the remote workers. Those are run, client.run, and client.run on scheduler. This client.run allows you to run any function you want on your workers, and client.run on scheduler does, as you might imagine, the same thing, but you can run any function on the scheduler. So here I can run os.pid to get the process ID for all my workers. I'll run it, and here it is. This is the process ID for all of my individual workers here. Worker also accepts a workers keyword argument where you can pass in the addresses. So you can say, I want to, only run this function on certain workers. So you can do that. Let's say I just want to run it on the first 2 workers, pass it in. I'll only run that PIV function on the workers that were specified. You can also, you can run custom functions that you define. And if they happen to have a Dask worker parameter for the function, it will actually, whenever it runs on a worker, it'll pass in the Python object worker, like the class instance there as well. So you can then inspect things like in threads and executor directly. So you can do that. Similar thing for run on scheduler. You can run a function on the scheduler to see what the process ID is. You can also pass in, if your function you're running has a Dask scheduler parameter, it'll pipe in the actual scheduler object. So all the stuff we did before where we were inspecting the tasks and worker states in the scheduler locally because we had the local cluster, you can do the same thing on remote clusters here via something like this. I'm going to run this function, which takes the Dask scheduler, loops over the tasks dictionary, returns the total, the sum of all the bytes that are in the workers. And there's the answer. So now that we know how to inspect, we now know how to inspect schedulers and workers directly using the local cluster, we can use client.run and client.run on scheduler to do that same exact thing on remote clusters as well. And here are some relevant documentations for the Dask worker and some information about all the state that's stored on the scheduler. And then in the last couple minutes, I wanted to talk about extending the functionality of workers and schedulers. So far we've only talked about kind of like inspecting the state, like seeing what tasks are on what workers, how many things are the workers processing, kind of just looking at the state, but not really extending any functionality. To do this, Dask has actually 2 plugin systems, one for the scheduler and one for the workers. And what these allow you to do is hook into certain things, certain like life cycle events that happen throughout the life cycle of a worker or a scheduler. So for instance, when the scheduler starts, you can run a custom method. When a new worker attaches to the scheduler, you can run a custom method. Here I'm looking at the documentation for these plugin systems. Basically, there is a base class, a scheduler plugin, and a worker plugin base class. And we can look at the various methods that are on these 2 classes. And these are the custom methods that you could implement. By default, like the base class just has no ops for all of those methods, but you could write a custom function that happens whenever you like add a client or remove a worker onto a scheduler, or whenever a task transitions on the worker from processing to in memory, you can run some custom functions here. I'll sort of I'll let you check out the documentation themselves for the actual signatures of these functions. But like, for instance, here is the worker plugin, and the transition gives you the key. The function signature should be the key of the actual task that's doing the transition, the starting state, which could be processing, the finishing state, which could be memory, and then various keyword arguments that depend on the actual transition that's happening. If it's going from processing to memory, or memory to, or like processing to error, or whatever the case may be, there will be some transition specific keyword arguments there. So one quick example is to make a counter object. So here we are creating a scheduler, our own custom scheduler plugin that just literally keeps track of the number of successfully completed tasks. So here we are we're instantiating. Initially, when we instantiate this object, in tasks will be 0. We then are checking whenever on the scheduler any task transitions between if the starting state is processing and the finishing state is memory. So it went from transitioning from I'm processing this thing to I have finished this thing and it's in memory. I'm going to increment in tasks. This will just tell you the total number of tasks that you've actually successfully completed. So to actually attach this plugin to your scheduler, what you can use is the scheduler's add plugin method. So you create a local cluster or some other cluster that you'd like. You can then instantiate the counter plugin here and then add the plugin to the scheduler like this. And we'll see initially the number of tasks is 0. I'll then go ahead and submit some tasks. Like the actual tasks themselves don't matter. I'm submitting things that happen on the cluster. And now we can see in tasks is 27, which corresponds actually to the number of tasks that I submitted to the cluster. So that's how one goes about creating a sort of simple scheduler plugin. I guess the last thing I'll do is there is an exercise which we won't have time for. So the last thing I'll do is show an example of maybe a more real world plugin. So Dask has a couple of built-in worker plugins, one of which is pip install. So we'll speak of Jupyter things, you can do question mark, and it'll display the source code for this thing. So you can see here is here's the source code for the pip install worker plugin. So we inherit from the worker plugin base class. And what you can feed this in is a list of packages that you would like to install with pip on your workers and some options. Like you don't have to specify any options, but you can pip install, upgrade, pip install, specify some custom index, whatever you would like to pass through the pip command. And here we're hooking into the worker plugin setup method. So this method will get called whenever a worker spins up. Whenever a worker is started, we will call this method at that point. And you can see we're doing, basically we're using subprocess.popen to call pip install with the options and packages you specified. There's some other stuff down here to like make sure if pip install fails, you get like a nice error. And if there's some stuff happening with the nanny, or if you want to restart your workers, sometimes pip installing things requires you to like go out of your environment and back in. This will do that for you. So anyways, this is like a nice example of a more real world worker plugin that would actually be useful for you to install some package automatically on your worker whenever it spins up. There is an exercise here that we don't have time for. I do recommend going through it if you like. This is just to keep track of the start and stop times for all the tasks, something a little more involved than just the number of tasks that compute on your cluster. Okay, and with that, I'll point out some additional resources. Here is the source code for Dask and distributed, as well as the documentation for Dask and distributed. If you have any Dask usage questions, feel free to use the GitHub discussion board linked to here. If you run into a bug or have a feature request, feel free to file an issue in the Dask issue tracker here. If you're interested in getting involved with Dask in the development process, feel free to engage on GitHub, and here is a link to our contributing guides. Yeah, with that, I'll say thank you all for attending this tutorial, and we really appreciate all of the time you took and you're having your attention for this 2.5 hours. So appreciate that. Julie, did you have anything you wanted to closing comments?
No, I'm all good. Yeah, thank you all for showing up, and I hope you learned something.
All right, thanks everyone.
Thanks so much, James.
Thank you.
Julia. That was awesome.
Thank you very much.